Before we close this section on procedures and stacks, let's talk about how things change when we go to the 64-bit architectures popular today. So the calling convention in x86 64-bit architectures is a little different, and that's because of the doubling of the number of general purpose registers. There are so many more registers available on the 64-bit architectures that we can decrease our use of the stack and make better use of the registers. So we're going to store arguments in registers, and we're going to store temporary variables in registers. Of course, we could always run out of registers, and we'll fall back to the way we did things in the 32-bit architectures we've just seen. But for the most part, we're going to try to make use of those registers as best we can and avoid the use of memory. So let's take a look at the registers in the 64-bit architecture again. There are now 16 general purpose registers, and they are 8 bytes each rather than 4 bytes, because we have quad words instead of 4-byte words. We're also going to extend our callee and callee saved and caller saved conventions, and you can see the registers are annotated here in green being the callee saved registers, and in yellow are the caller saved registers. Also, we're going to use 6 registers in these locations for passing arguments, and we're going to use up to 6 registers to take care of 6 arguments for a procedure. Now, if we have more than 6 arguments, we'll have to go back to using the stack. But for the most part, we'll use these, and most procedures have just a couple of parameters, so most of the time we won't have to use the stack. We're still going to use RAX for the return value of a procedure, and we're still going to use RSP for a stack pointer. Okay, let's revisit the swap function and look at it in both the 32-bit architecture, which we see here on the left. This is the one we've seen so far, and a swap implementation using 64 bits. Okay, and the differences in these two cases are that arguments are passed in registers. So the first argument is now in the register RDI, the second in the register RSI, and that's where we find the 64-bit pointer, those 2 arguments to swap. So we're not having to get them off the stack. So the only stack operation we really need is return. That goes and gets the return value from the stack and jumps to that location when we're done. By avoiding the stack and holding all the local information in registers, we can make execution much faster. One, because we have less instructions. As you can see, we have quite less instructions for the 64-bit version, but also because we're not going to memory. And the stack is stored in memory, and that is slower to get to than the registers of the CPU, the general purpose registers. We'll learn more about that later when we talk about the memory system. But for now, suffice it to say that it's a lot faster to go to registers. Okay. So the highlights of this then for the 64-bit case are that arguments up to the first 6 are stored in registers. It's faster to get to those values there than if they were in memory in the stack. Local variables can also be placed in registers if there's room, and we don't have too many of them. Otherwise, we will have to go back to the stack. We have a call queue instruction now instead of a call instruction, which puts a 64-bit return address on the stack. And of course, it will have to decrement the stack pointer by 8 rather than 4 because we're putting 8 bytes on the stack. We also have eliminated the use of the frame pointer. Remember EBP, our base frame pointer. We're not going to do that anymore, and we're going to make all references relative to the stack pointer. So we won't have to keep track of 2 registers pointing to the stack, but only 1. And EBP, or now its 64-bit version RBP, is going to be available as a general purpose register. And the reason that works is because we can access memory up to 128 bytes beyond the RSP, where RSP is pointing, without having to use multiple instructions. We can do that directly. This is called the red zone, okay? And so we can store these temporary variables on the stack very easily and access them quickly. The registers are still designated as caller saved or callee saved, however, but slightly differently than they were before. Okay. So ideally, the 64-bit architecture has no stack frame at all except for the return address. So we've now shrunk the stack frame down to just one piece of information, namely that 8-byte return address that is placed on the stack. This makes things a lot simpler for manipulating the stack and making the frames that we need. However, we always have to fall back to the 32-bit architecture conventions if we can't fit things in registers. And that's why we bothered to show you all that 32-bit stack convention, even though we're mostly running on 64-bit architectures these days. Because when we have too many local variables, we have to go to the stack. When local variables are more complex data structures like arrays or structs, we'll have to put things on the stack. When we have an address for a local variable, we'll have to put it on the stack because we can't have an address to a register. We have to have an address to a memory location. So we will have to put it on the stack. And whenever we need more than 6 arguments to a function, we'll need the stack again. And of course, saving registers away. That also will potentially have to have us use the stack. So we still need stack frames, and it's still important to understand the general case, but keep in mind that most of the time on 64-bit architectures, that stack frame is tiny. It's just the return address. All right, let's take a look at an example that illustrates this. We're going to have this function called callproc, which does has some 4 local variables of different sizes, and then does a call to another procedure called proc, and then finally returns a value that it computes according to this expression. Okay, so the way callproc is going to start, of course, is its stack pointer is pointing to where it has to return and whatever procedure called it. That's the top of the stack. And the first thing that it's going to do is allocate 32 bytes on the stack for the local variables that it will need. And you'll notice that by adjusting the pointer down 32, the stack pointer is now down here. 32 is 4 times 8 bytes, so 4 8-byte words. That's why I've drawn it as 4 horizontal sections of memory. Each of those is 8 bytes. And we're going to allocate the 4 temporary variables, x1 through x4, to these areas here. And you'll notice that x1 occupies 8 bytes. It's a long integer. x2 is just a regular integer, only needs 4 bytes. x3 is a short int, which only needs 2. And x4 is a single byte. Okay. Now, why did we allocate 2 more words? Well, we're going to see we're going to need those because this procedure call here has 8 arguments, more than the 6 we can do with registers. So we're going to need 2 places to go put those 2 extra arguments for our procedure call. All right. So let's see what the first instructions of the function are. As I mentioned, we adjusted the stack pointer by 32 to create that space. And then we moved 4 values into different locations on the stack. And you notice that we used offsets to the current stack pointer to find the right places to put them. We put the 8-byte quantity, the quad word, that was value 1 for x1 at 16 plus the stack pointer. That's at this location. Then we moved a long word, value 2, to 24 plus the stack pointer. That's at this location. Then a word, or rather 16 bits, value 3, at 28 plus the stack pointer. Well, 24 was here, 4 more over puts us here at x3, and then finally a single byte of value 4 at 31 plus the stack pointer. That's that 24 here, and then 7 over puts us over at where we've labeled x4 as byte, that single byte. Okay. Let's move on now to setting up the parameters, the arguments for calling the function proc. Okay, that's the next part of this procedure. And what we see here is a set of instructions that set things up for all those arguments. Now, arguments are passed in a particular order in registers. The first argument has to go into RDI, the second into RSI, the third into RDX, RCX, R8, R9, until we got six arguments. The rest are going to go on the stack. Okay? And that means 2 more will have to go on the stack in this case because we have 8 arguments. So let's take a look at the first instruction. It moves a quad word with value 1 to RDI. That's the equivalent of putting that x1 there as the first argument. Then we are going to need the address of x1. Well, the address of x1 on the stack is here at 16 from the RSP. So you'll notice that we'll calculate that effective address and put it into RSI, the second argument. Then we'll put a value 2 into EDX for the third argument, and the address of that value, which is at 24 plus RSP, into RCX, that address for x2. Then we'll move a 3 into R8D. That's just the 4 bytes, the low order 4 bytes of R8. That's how we refer to it. And then put that address, in the address of x3 into R9, our 6th argument. And 28 plus RSP is the address of this byte right here. Okay. Lastly, we'll move 4 into where the RSP is pointing right now. Remember, the parentheses are dereference to that, and that's argument number 7 put onto the stack at that location. And then, of course, the last argument, argument 8, is the address of x4, and the address of x4 can be computed by doing 31 plus the RSP. We're going to put that in RAX temporarily, just so that we can then move it to 8 plus the RSP, the slot for the 8th argument. Okay, so now we've set up all 8 arguments, 6 in registers, 2 on the stack, and we're ready to call proc. At this point, of course, a new return address gets pushed onto the stack. That will help us come back to this point in this procedure, call proc, after we're done with the proc call. Okay, once that's completed, we will be back here and now have to do that computation to figure out the return value. So how do we do that computation? Well, what we're going to do is make sure we carefully get the values of our temporary variables in this procedure and put them into registers with appropriate sign extension. So we're going to be using these interesting instructions here that say move. The S stands for extending the sign bit of the word into the long. All right? So we're taking a 16-bit quantity, the word, sign extending it to 32 bits, the long. Okay? That's what the L refers to. And the S says sign extend. Another option is Z, for just put zeros there in the other 16 bits. But this says do the sign extension. And the result goes into the 32-bit register EAX. We'll do the same thing for now, a byte extended to a long to get the value of x4 and put that in EDX. sign extended, and then subtract that from EAX. So this will have computed x3 minus x4. Now, of course, that's a 32-bit quantity, and we're going to have to multiply it with some 64-bit quantity. So we're going to do some more sign extension using the CLTQ instruction. That sign extends the 32-bit EAX register to 64 bits. The next part computes, as you can imagine, x1 plus x2, and it does that by getting the value of x1, moving it into RDX, or rather the value of x2, moving it into RDX and sign extending it to 64 bits, in this case from a long to a quad, and then adds the already 64-bit value of x1 also to RDX. So here we will have x1 plus x2 now as the result. Finally, we take those two registers, RAX and RDX, and do a multiply instruction to compute the final result. Okay, the result is placed into RAX, ready to be returned. Remember, we put the return value in the RAX register. The last thing we need to do before executing our return statement is clean up the stack and get rid of the space we allocated while we were in this procedure. And to do that, we add 32 to the stack pointer, the opposite of the subtract 32 we did at the beginning. Okay, so now we are exactly back to a stack that looks just like it did before, and we are ready to execute the return instruction that will take us back to whatever call proc in the first place. So to summarize, the 64-bit architectures make a heavy use of registers because they're faster than using the stack in memory. We use them for parameter passing, and we use them for temporary variables. Okay, so there's a minimal use of the stack. Oftentimes actually, we don't use the stack at all except for the return address of the function. And but when needed, when we need the space there, either for those arguments or for more temporary variables, we allocate and deallocate the entire frame at one time. It's just faster than doing multiple pushes and pops. So we don't bother with a frame pointer anymore and address everything relative to the stack pointer, as you saw in that previous example. Okay, this also creates a lot more room for compiler optimizations that can play with the registers and how we use them and best make use of them, so we don't have to have collisions that would cause us to have to save registers and so on. All right, so that ends this section, and I hope it provided a good overview of procedure call conventions, both for 32 and 64-bit. Remember that although we make minimal use of stack frames in the 64-bit architecture, we often have to fall back to the general case, which we saw with the 32-bit conventions.